Hello everyone, welcome back to the course on architectural design of ICs. So, in the last few classes we are seeing that different multiplier architectures. Okay. So, different multiplier architecture for different purposes, that means considering the speed for high speed operation, for low power consumption or low area consumption. So, that till now we have seen this tree multiplication method, then Booth multiplication method, how we can, that means combination of Booths and then tree multiplication, that we have also seen. So, and then we have seen that if we compare all the multiplier architecture. So, at that time we have seen that if we combine or the hybrid architecture, that means the multiplier architecture which are based on two different technique, that means suppose for Booth multiplier I am getting that area as the, that means advantage, whereas speed not that much, in compared to the Wallace tree multiplier architecture, where area is not that much efficient, but speed I am getting as the, that means advantageous. Okay. So, combining these two I can get one hybrid architecture where I can get the benefit of area as well as the speed. Okay. So, that we have seen. So, till now what we have learned or what architecture we have seen, all those are unsigned multiplication. Okay. So, now we will see this how to do sign multiplication. Okay. So, to before to start with sign multiplication, we will just start with that means just one review, a quick review about the signed addition method, because multiplication is nothing but the addition operation. So, we will go through one quick review of the sign addition operation, then we will start this sign multiplication method. Okay. So, this multi operand signed addition. So, thus far we have considered only this unsigned multiplication, the data structure which are for used for unsigned multiplication. Now, we will that means try to review this, what happened whenever we do, or what changes happened whenever we do sign multiplication. Okay. So, these things we have already seen that in case of signed unsigned multiplication, that we do not have to bother about the sign. Okay. But in case of the sign multiplication, what we have seen in Booth multiplier. So, in those case what we have to do, we have to extend the sign, okay, because otherwise the corresponding in multiplication what we are doing? We are doing that means for the first partial products it is same as the, or that means the bitwise ANDing operation with the 0, that means LSB of the multiplier bit. Okay. Then the corresponding next bit or the next bit position, for the next bit position what will be the corresponding multiplicand value, that will be one bit shifted and then it will be added. But at that time whenever we are doing the shifting, at that time means what? We are increasing the length in the MSB side from the partial product 1. Okay. So, in unsigned multiplication we do not have to bother about what is the sign which is for partial product 1, but in case of sign multiplication we have to be bothered about that. Okay. So, that is why here you see in this particular example, suppose this is the magnitude position and this is the sign, then this sign has been extended to this to fill all this that means vacant position which we have not considered in case of unsigned multiplication. Okay. So, when we are adding two numbers, it must be sign extended to the final results with, okay, and then add together using the adder technique to avoid the, that means, or to get the proper results. When adding these multiple numbers, must sign extended to final results with and then add together using adder technique, this can dramatically increase the size of carry save adder. That means, as initially for unsigned multiplication what was there, this position was vacant. So, as I am increasing, that means filling with this extended bit sign bit position. So, that means I need more number of adder, this position I should add, I have to add. Okay. So, addition of those require adder operation, whether that is full adder cell or half adder cell. So, I need adder. So, that means this will increase the size of the carry save adder or full adder cell if I say. So, the 2's complement basically that has been represent or that has one negative weight method. Okay. So, what is negative weight? In 2's complement format, whatever is the MSB that has been considered as the, that means the weight for that is minus. Okay. So, that means if I suppose this 10011, if I consider this in 2's complement format, so at that time this number will represent minus 13. Why minus 13? Because this is 5 bit. So, the positions of the bit or the weight of the bit will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and the MSB position will be minus of 2 to the power 4. Okay. So, now as I am getting 1 at this particular position, so this is minus 16 and then the corresponding 1 1 for 1 1 this is 3. So, 16 my plus 3 that is equals to minus 30. Okay. So, now for the same case if I am getting 0 1 0 0 1 combination, that is also in 2's complement format if I represent. So, because of this 0, this represent that this is one positive number. Okay. So, positive number means to this position is 0 means this is no negative values are there. Okay. So, that is why this position is 1. So, 2 to the power 3 that is 8 and this position is 2 to the power 0 1. So, that means the value of that this particular number is 9. Okay. So, that means in 2's complement, but if we do not use this 2's complement number representation. So, at that time what will be this value? This will be 16 plus 3 plus 1, the value will be 19 in case of unsigned, that means the signed representation. Okay. So, that is the difference between signed representation and unsigned representation. Then 2's complement sign extension method, how we can do to extend to sign extend a k bit number by 1 bit. How to do that? That is the first step is that instead of making the MSB have a weight of minus 1, consider that the digit has a value of minus 1 which does not exist in hardware, because this is just for the notational purpose. Okay. And then in the second step apply this equation where this basically this xi dashed represent the inversion of xi bit. In original representation, complement the sign bit and add 1 to the sign bit column and add negative 1 to the column k. So, actually this is the step, and in third step now remap the new sign bit such that the weight is minus 1. So, this is the basically steps are involved to how to extend the sign bit. Okay. We will see whenever we will take the or consider the example. So, at that time it will be much more clear to you. So, if we consider the sign tree multiplication, so at that time how we can do this sign tree multiplication. So, at that time, so this is the sign position and this is the magnitude position. Now, this extended whatever is this value sign, that has been extended to the corresponding width of the final result or width of the product. Okay. So, then this what it says, recall for 2's complement multi-end operand operation must first sign extend all partial products to result bit width and then add. Okay. So, what we have done, we have extended the sign to the final results, all the partial products has been extended up to what? Up to the results, final results bit width. And this can be wasteful in terms of extra full adder cell requirement. Then two solution can be that means proposed, or two solution can be introduced to solve this problem. Remove redundant full adder cell for sign extension, or use negative weight representation, which is basically follows this Boguli multiplier. Okay. So, what is the architecture for this Boguli multiplier, that we will see now. So, how to remove this redundant full adder cell? How to remove this? These are the signs, okay. And then 5 redundant copies can be removed. Actually, we have seen how we can reduce these particular terms, that we have seen in the last class. We have already discussed that. That is, if I am representing this particular number in 1's complement, then the sign will be, for the first partial product, it will be extended by 3 position, that is S bar, S and S, okay. And if I am representing this number in 2's complement format, then I do not have to add the sign to the LSB position, but if I have not done that, at that time I have to add the sign bit to the LSB position. And for the rest of the case, what it will be 1 and S bar, and at the last partial products it will be just as it is. So, before to the last it will be just the S bar only, not 1 and S bar. So, that we have already seen in the last class, we have already discussed this, how to remove this. Okay. So, then apart from that, there is another method how we can do. So, suppose this is the 2's complement multiplication format, okay. Suppose this is the A and this is the B. So, the corresponding MSB of A, this is represent in 2's complement as these 2 multiplier and multiplicand both are represented in 2's complement format. So, at that time the MSB of that represent minus A4, and the multiplier, that means MSB, that represent minus x4. So, now bitwise ANDing operation if we do, then for this I will get minus A4 x0, then for this minus A4 x1, for this position A4 x2, this is minus A4 x3, and for this final, that means this, for the fifth one, all this will be minus except from this, because minus minus it is plus, and rest of the that means multiples, they are in negative. Okay. So, now in basically in hardware, whenever we will design the hardware, so at that time how I can represent this as minus. Okay. So, what is the technique to represent this particular bit? Okay. So, there is actually if we follow this Boolean algebra, so at that time I can write this z bar equals to 1 minus z, or z equals to 1 minus z bar. Okay. So, now for this particular case, whenever I am getting minus A4 x0, so that can be written as, if I find that okay minus AJ xi, so that can be written as AJ, so xi can be written as 1 minus xi bar. Okay. So, then it will be what, plus AJ xi bar minus AJ. Then again this AJ can be, minus AJ can be written as AJ xi bar plus AJ minus 2 AJ. So, this minus AJ xi, this can be represented as this one. Okay. So, why I have to, or why I have come down to this particular equation, there is one intention to do that, because if you remember, so at the very beginning whenever we are talking about this sign addition operation, at that time we have seen that in the second step of extending the sign, we have seen that we can represent the number, negative number, in terms of xi bar plus 1 minus 2. Okay. So, if we just see this particular example, so we have discussed that this particular equation xi bar plus 1 minus 2. Okay. So, if I follow this particular equation, this is also nothing but, this is also same as that one. If I take common of AJ to everyone, so at that time how it will be, xi bar plus 1 minus 2. So, that means I can represent this number as same as whatever equation I have represented there. Okay. So, in this manner I can represent. Okay. Now, for that particular position, suppose for minus A4 x0, now minus A4 x0, that can be represented as how? How it will be represented? So, minus A4, then A4 x0 bar and A4. Why is so? Because here you see minus 2 AJ. So, this is minus AJ xi. Okay. So, this particular bit. Okay. Now, suppose I have to, that means if this is, if I consider for the next, that means for this, if I consider this as A4 minus A4, suppose this is x0. So, this can be right. Now, if I represent this particular equation in terms of this j and I, so at that time what it will be? It will be A4 x0 bar plus A4 minus 2 A4. So, minus 2 A4 means what? It is, it will come 2 of A4 means what? It is just left shift by 1. Okay. And what is the corresponding weight? That is minus. So, as this value is minus, so that means it will be, the weight for that will be in minus. Okay. So, that is why, in this particular minus A4 x0, that can be represented as whatever we have seen in the minus A4 x0, that will be A4 x0 bar plus A4 minus 2 A4, right. So, this can be written as, so minus 2 A4, 2 A4 means, so this is the position where I will get A4. So, this is A4 x0 bar and plus x A4 means, so this is the position. So, it is just like the same. This equation can be represented as this one, if I, because this has the 2 bit shift weight. So, this minus A4 over here means this is minus 2 A4 plus A4 x0 plus A4. So, this equation can be represented as this one. So, same for this A4 x1. So, A4 x1, for A4 x1 what it will be? Minus A4 over here and A4 x1 bar over here and A4. Then again for this particular case A4 x2 minus A4, A4 x2 bar A4. For this one minus A4 x3 minus A4, A4 x3 bar A4, correct. Now, if I just add the corresponding position wise addition operation. So, at this particular case what I am getting? At this particular case A4 x0 bar A4. Okay. Then this at this point, at this particular case, so minus A4 plus A4, it will be balanced. Okay. So, only what I will get? I will get only A4 x1 bar over here. So, at this particular case what will happen? So, A4 bar, sorry, minus A4 and plus A4 will cancel each other. So, I will get A4 x2 bar. So, same as this particular position. So, it will be A4 x3 bar. And for this minus A4, okay. So, this is minus A4. So, minus A4 can be written as A4 bar minus 1. Okay. So, because of that particular equation, okay. Z bar equals to 1 minus Z, or Z equals to 1 minus Z bar. Okay. So, that means A4 bar means that is nothing but A4 bar means if I just consider this minus of A4. So, that can be represented as minus A4 minus 1. Okay. So, then if I just consider that means what I left? The last position. That means this, the last partial products which I am getting, so this one. So, this one is left. So, how I can represent this? So, this can be represented as, so minus A4 x4. So, the as same as x4 minus x4 at this particular position, A4 bar x4 and x4. So, here x4 is common, A0 is basically changing, right. So, that is why keeping in the previous case what we are doing, that A4 was common in each of the multiples, whereas the values other values x0 is basically changing. Here x4 is common and A values are changing. So, that is why this x4 is basically coming over here. So, minus x4 A0 bar x4 x4. Okay. So, on the same way here in this particular equation I can write as, or I will come down to this equation, that is A0 bar x4 x4, V1 bar x4, A2 bar x4, A3 bar x4, x4 bar minus 1. Okay. So, now on that particular equation, now these values will be replaced. If I replace these values on that sign multiplication, whatever multiples we are getting. So, now after, that means replacing these values, what will be the final equation? Okay. So, if I consider, so at that time this 2 to the power 8 position, that is minus A4 minus 1, this is for whenever that means A4 is common. Okay. So, minus A4 minus 1, A4 x3 bar, A4 x2 bar, A4 x1 bar and A4 x0 bar along with A4 at this particular position. And for the minus x4, where for that means x4 is common for it and A value is changing. So, at the time for that particular equation, whatever I will get, that is minus x4, A3 bar x4, A2 bar x4, A1 bar x4, A0 bar x4 along with x4 at this particular position and minus 1 at this particular position. Now, you just combine this all this, that means equations. So, at that time what I will get at this particular position. Okay. So, A4 x0 bar and A0 x4. So, A4 x0 bar and A0 bar x4. Okay. And then A4 and x4, A4 and x4. So, this position is A4 x1 bar, A1 x4 x4. So, this is this. So, this will be added, this will be added, and for what will happen for this particular case. So, A4 bar and x4 bar will come here. So, minus 1 and minus 1, that will give me minus 2. So, again minus 2 means what? Minus 2 means it will come to the, or that particular bit will shift to the next MSB site. Okay. So, then this minus 1 will come at this particular 2 to the power 9 position. Okay. So, that means minus 1 means this is nothing but with negative weight. So, this if this bit is 1, so this will be minus 2 to the power 9. Okay. And then rest of the, that means equations are something like this. Okay. So, now this can be, now this particular equation, now that can be replaced as this one, that means at this particular position what is the value I am getting, that is A0 bar x4, where this is A4 and x4 are added at this particular position, and here you see A4 x1 x4, A4 bar and x4 bar along with 1 at the 2 to the power 9 position, which is minus 2 to the power 9. Here you see that is minus 2 to the power 9, as I am getting 1 over here. So, this position will give me minus 2 to the power 9. Okay. So, this is the Bogli-Tooth complement multiplier circuit, or the, that means operation or the principle of operation of this Bogli-Tooth complement multiplier architecture. Okay. So, now my point is that can I reduce this. So, that means for this, for the how this is basically different from the normal this unsigned multiplication? If you see that in the middle position, if I do not consider this sign extension, so at that time I will get only the multiples up to this, that means from A4 to this, that means the 5 over here. Okay. But two extra, that means multiples are coming which are A4 and X4 because of considering the 2's complement number representation. That means I am increasing the depth here. So, initially the depth was 5 here, but here now it becomes 7. So, that means if I am increasing the depth maximum of all the, that means possible combination. So, as I am getting the maximum depth over in this particular position, that means I am increasing the delay for this particular multiplier. But the thing is that as I have considered this 2's complement number, that means multiplication method, or I have a multiplier which will give me or which will produce the results in which are in 2's complement number representation. So, at that time I need to do this. There is no other way out to remove or to, that means not to use this A4 and X4. So, I have to use this to get the proper result. Okay. So, then my point or my observation or my focus will be how to reduce this length. Okay. Whether I can do that, if I can do that, then how I can do that. Okay. So, that we will discuss on the from the next class. Okay. So, for today this is it. Thank you.